brief moment and then make you fuzzy. It's because I got old enough that my glasses, I only need them for distance, but now they're so strong I can't reach stuff up close. So I didn't realize it was going to be that way till I had them. So yes, and now also I only get glasses like once every 8 years, so. Okay. So just to remind you guys, I don't expect all of you will have much familiarity with what I'm going to do, and that's fine. So I've told some of you this. I think one of the most important lessons to learn as you're beginning to get into research is how to compartmentalize a problem you're working on, a little compartment around what you understand, and then everything else that you don't understand, and become comfortable with the fact that you just don't understand it and you don't need to understand it. Because otherwise you're going to go down a rabbit hole of trying to understand all these things that you just don't yet have the knowledge to understand. And you get stuck in research and you will flounder. The word we use in English is flounder, meaning you'd make no progress. You're making a lot of effort, but you're not making any progress. It's universal. It's students everywhere are like this. It's a rare person who naturally, I think, understands how to do that. Because we're doing physics because we want to understand. So if there's something you don't understand, you want to try to understand it. But if you want to make progress on research, you have to accept the things you don't understand. The person giving you the research problem understands that you don't understand them, and they want you to work on the part that you can work on. And slowly, the bubble of what you understand will get bigger and bigger and bigger. And as someone else aptly asked, of course, you should attempt to try to figure out the things you don't know, but don't let it slow you down on the things that you do know. And the reason I'm saying that is, even if you don't understand what I'm doing, what I'm trying to provide for you today and tomorrow will be a recipe of how you go from Lagrangian to amplitudes. So even if you don't understand it, write it down. It will be correct. Hopefully every single sign and factor of 2 will be correct. And it's an algorithm you can learn to apply to doing quantum field theory calculations. Okay. I was going to talk about the strange quark a little bit because this whole chiral perturbation theory can be extended to the mass of the strange quark. I'm just going to skip most of that, though, and get to the other stuff because I want to get into the loop integrals, which I still may not do today. I'll just say, if you add the strange quark, and just to put up the standard in case you haven't written it down yet, and just to say again, if you have questions and you send questions and you don't get a reply, another thing to learn how to do is be, what we say, proactive. After a week or whatever, send it again. Hey, just a reminder, I asked you. Until we say, stop asking me questions, just keep gently reminding that, take initiative is another way we say it. I don't know, you must have a similar expression in whatever your natural language is. Take initiative, be proactive. It's also rare, I think, for people to naturally be proactive. And so if you are, you will more likely succeed in whatever you do, physics, but anything else in life. Okay. So when you have the strange quark, then you get 8 Nambu-Goldstone bosons. And these are all in units of MeV. And then there's these kaons. And there's something interesting in the kaon sector. It's the K0 and the K0 bar. There's 2 of them. You'll notice the pi plus is heavier than the pi 0. Do you guys have a feeling why that is? I saw your mouth move, but I didn't hear anything. electromagnetism. So why isn't the K plus heavier than the K0? It can't be the only story. There's another source of isospin breaking, like I mentioned yesterday, is the quark mass splitting. And what you'll learn is in the pion sector, the quark mass splitting can't contribute to the pion mass until MD minus MU squared, second order in isospin breaking. Where the and that's because it's an isovector quantity. Whereas the kaon is an it's an isotriplet. The kaon is an isodoublet, and in fact gets a linear correction from MD minus MU. And the down quark is sufficiently heavier that that's what, even though the K plus has a QED correction, the down quark mass contribution wins and makes the K0 heavier. And then there's the eta. And remember I said the ultraviolet scale in chiral perturbation theory is this quantity 4 pi, and I said F pi. And this is a number that's like 92 MeV. So this is roughly 12. So this is like 1100 MeV. And so you might ask, you should ask, are these numbers sufficiently small such that mk over lambda chi gives you a good small parameter? No. In the meson sector, you'll see it always will show up as the square of that ratio. So the square of a half is a quarter. Maybe that's okay. And in fact, it works pretty well phenomenologically. There's these decay constants you can compute and measure experimentally. The ratio is about 1.2. So what is that telling you? That tells you, and at leading order, the important thing, I was going to work through this, but I'm not going to. At leading order, the decay constant that shows up in this theory is the same for the pion and the kaon. So the ratio is exactly 1 at leading order in the effective field theory. And so that gives you a guide that, the next to leading order corrections, so I'll write this word out here. We often say stuff like next to leading order, and we shorten that as NLO. And then if you go to second order, then we start doing stuff like this, N2LO and NLO, and so on. So when we talk about leading order, next to leading order, et cetera, this will make more sense as we go along. But this is a order in the small expansion parameter of the effective theory we work to. And so this is a guide. So this says next to leading order corrections have to be at least 20%. And if they are, N2LO corrections you expect to be 4%, which sounds okay. But the problem is this is a one-loop calculation, this is a two-loop calculation, and precision comparisons with experiment in theory requires sub-percent precision. So 4% doesn't cut it. And no one's going to do a three-loop calculation for this theory. So the effective theory with strange quarks works well phenomenologically, qualitatively, but it's not good enough for precision comparisons with experiment. So people have actually constructed a two-flavor theory for kaons, where you treat the strange quark as heavy and you only look at the light pion degrees of freedom excitations about these strange matter particles. All right, now let's add the quarks. So last time we did the kinetic Lagrangian, let's add the quarks in. And just as a reminder, our QCD Lagrangian has this left-right symmetry between the kinetic operator, and then there's the quark mass operator that breaks the chiral symmetry explicitly. So how do we understand these effects in the chiral Lagrangian? So what we do is first, you promote the mass to a source. You can do this theoretically. You know, in experiment, you can't do this, but theoretically, you can promote the mass to a scalar source, which actually has space-time dependence. So that means the term in the theory will look like psi bar left S, psi right, I guess everything's at X. And we talked about differentiating the partition function, which again I know is a concept that's not familiar to everybody. But what you can imagine doing is then taking functional derivatives with respect to the partition function of the source. And what that does is it brings down the psi bar psi operator into your correlation function. I think we talked about this Tuesday a little bit, taking these with the, in that case, is with the axial current, differentiating with respect to the source. And then the next thing we do is we say, well, I know the mass only is small compared to lambda QCD, so if I want to treat it in perturbation theory, why don't I, for the moment, pretend that it transforms under chiral symmetry transformations such that when I combine it with these fields, it actually provides an operator that's invariant under chiral rotations. So what we'll do is we'll let S, if I put S here, transform as R, S, L dagger. And then S dagger will transform as L, S dagger R. So then my operator, this one gets the S dagger. And so now, as you can see, if I have psi bar right, S psi left, and I do a chiral transformation, you get psi bar right, right dagger, right, S, L dagger, L. And those are the identity by construction, and so you get back the operator you started with. This is called spurion analysis. I don't know where the name comes from, but I know that's the name. Maybe I'm going to speculate. It's because it's a spurious symmetry. It's not a real symmetry. So for the moment, I pretend like it's a symmetry. And then when you start doing calculations and you set the quark mass equal to the values of the quark mass on the diagonal and zero everywhere else, that you're taking the act of explicitly breaking the symmetry. And this way you can track how that symmetry breaking encodes itself in the low energy effective theory. So when we do that, we get to add to our chiral Lagrangian another operator. So we have our kinetic term, as you recall. And now I'm going to add another operator. I'm going to call it chi sigma dagger plus sigma chi dagger. What is this chi? Chi is equal to 2bs. And to be consistent with what I did over here, I'm going to flip where the dagger is. So this guy is now the dagger. So I just don't have to change the rest of my notes. Okay, now what is this? B is a number, a dimension 1 number. Why do we know it's dimension 1? Our mass power counting of the operator. I have F squared, which is dimension 2. S is going to become the quark mass, which is dimension 1. I need a dimension 4 operator. Therefore, B must have dimension 1 as well to get dimension 4. The choice to put F squared over 4 is just because I know in the end what the answer is going to be. So now what we want to do is ask questions like, well, what is this B quantity and what is the mass of the pion? Let's start with B. So I was talking about differentiating the partition function. So this is, again, matching. I have my QCD partition function as a function of my source. We're going to, just for shorthand, use big phi to represent all the fields, the quarks and the gluons, some big path integral. So I'm hiding the fermionic nature of the quarks in here, but I trust you remember this from Amy's lectures. And then I have my Lagrangian, or my action. So I have the QCD Lagrangian, which we have written over here, plus our quark mass operator. And there's also, of course, the glue, which is included in the QCD Lagrangian. And then at the chiral Lagrangian, Now I'm going to have to integrate over these sigma fields. And I have and again, the 2 in the Chiral-Lagrangian is reminding us we have 2 powers of the derivative. And as we'll see, the effect of the mass is going to be the same order. Now, without even me telling you why, does anybody have a feeling why the mass should be the same as the kinetic operator, as opposed to higher order? It's like if you have some particle propagating around, the lowest energy it can have is the mass. So that kind of sets the floor of the effective field theory. And then we want to explore dynamics where the momentum is of the order of the mass of the particle, because that's where the particles are kind of going on shell. When p squared is close to m squared, you're getting close to on-shell physics or low energy dynamics. And so then, in order to match, we need to match chiral perturbation theory to QCD. We're going to differentiate both of these partition functions with respect to the source term. And the point is, the source is independent of whether it's in an effective field theory or not. There's one and only one source. So by differentiating with respect to the source and then asking the correlation functions in QCD and chiral perturbation theory to be the same, that's how we can determine these low energy constants. So this is the active matching. You do the same thing in the electroweak theory when you integrate out the W and the Z boson. But there you can actually solve the theory analytically at the UV theory. Okay, so if we differentiate, and again, in the literature, if you use this symbol delta, at least amongst the books I've read and the people I've learned from, this is what we call a functional derivative as opposed to using the partial derivative symbol. And what the functional derivative means is, in addition to bringing down the source term, you get rid of the d4x. You have some delta function to put it at a very specific space-time point. So just remember that. Sometimes you can do partial derivative, sometimes you can do the full functional derivative. And what do we get? We have the same partition function, and now the difference is we have this extra psi bar psi term that comes down, because from the QCD Lagrangian, if I differentiate with respect to S, and now I'm going to be a little sloppy, and I'm just going to put an S in front of both, because I know at the end of the day I want to set it equal to the quark mass. So I'm just going to kind of mentally do that ahead of time a little bit. But if you're being more careful, you would keep these as S and S dagger. But for now, I'm just going to say, let's just differentiate with respect to S. So I get the full right, left plus left, right, which is why I've recombined it into just psi bar psi without a left, right. And then we have the action of QCD. And we know this is equivalent to the vacuum expectation value of the psi bar psi operator. Now we do the same thing in chiral perturbation theory. Thank you. I'm used to working in Euclidean space. So, thank you. In here, what do I get? I get minus f squared over 4, and then I get 2b. I'm pulling out b because it's a number. It has no flavor structure. Somewhere it's written down here. I lost it. Here we go. And then we have a trace of sigma plus sigma dagger. So in SU2, sigma plus sigma dagger is just the identity operator. So if you did the small field expansion, remember sigma is this exponential of I phi over f. So if you did the small field expansion, it's not obvious that sigma plus sigma dagger is the identity, but in SU2, this is the identity. And so then if you take the trace of the identity operator in SU2, you just get the number 2. And so then we get minus f squared. The 2 from here and the 2 from the trace eliminate the 4, so we get F squared B. And so then, by asking these correlation functions to match, we demand that they match because we demand the low energy effective theory reproduces QCD. What we see is then minus F squared B is equal to the quark condensate. And recall, we said this is our order parameter for spontaneous chiral symmetry breaking. Or, in other words, B is minus psi bar psi over F squared. And the dimensions also track. The quark fields are mass dimension 3/2, so you get dimension 3, F is dimension 1, so this is dimension 1 quantity. So this is what this quantity B is. And this is how you get the Gell-Mann-Oaks-Renner relationship. We're going to use this and now calculate the mass of the pion, and we'll see how that arises. So now let's just look at the mass term in the Lagrangian. So now I have set a density to the quark mass. It no longer transforms, so I can wrap it around the trace, and it's the same in front of both the sigma and the sigma dagger. So then sigma plus sigma dagger is what? Well, sigma is 1 plus I phi over F. Do the exponential expansion. And in fact, let me write higher order terms, and hopefully I'll remember to leave this up here for later. Now, you can look at this and see, the odd powers of the pion field cancel because they have opposite sign in the complex. And then you can convince yourself that all odd powers are going to cancel when I take the sum of the two. And so then what do we have? For the mass term, we just want to work to order phi squared, right? Because the mass operator has 2 powers of the field. And so the 1, actually, that's interesting. That gives some vacuum energy density. So if you take the 1, you'll get a non-zero contribution of 2b. This, I can take it out of the trace. You get F squared over 4, 2b, and then you're going to get mu plus md in the trace. And so this is the vacuum energy of QCD as well, written from the perspective of the chiral Lagrangian. Now, how about the mass term? Well, we get and the spurion analysis I just erased. This is a technique you can use for all sources of the theory. So we have an axial symmetry, a vector symmetry, a scalar density, a pseudoscalar density, and if you want to imagine adding operators from beyond the standard model physics, because you're interested in understanding how new physics would embed itself in the quarks and gluons and interact with them, you can create a source for that new physics and also do the same idea, this spurion analysis, and see how the operator gets built into the chiral Lagrangian. And that way you can use the chiral Lagrangian to study low energy dynamics of pions and nucleons to see how the pion or the nucleon or a kaon would respond to the presence of some new beyond the standard model operator. So you just have to make sure you build it in such a way that it respects the symmetries of the standard model, because You can add electroweak interactions to the chiral Lagrangian as well, and you do so consistent with all the symmetries of the standard model. And if you have some heavy new physics, such that it makes sense to treat it in an effective field theory where the standard model is the low energy effective theory, then you add these new higher dimensional operators, and then you can embed those operators into the chiral Lagrangian as well. And depending on how we go, I'll show you actually how that works for lattice QCD. You can add how does discretization effects get embedded into the chiral Lagrangian. But for now, let's go back to the mass. So what do we have? If I take sigma plus sigma dagger and I want the phi squared terms, we see the I squares to a minus sign. These two terms are the same. And I get two of them, so just the half goes away. I have my f squared over 4, 2bmq. So this mass Lagrangian contains the operator f squared over 4, 2bmq, and then I have a minus phi squared over f squared, if I got that right. And remember, MQ is going to be MU, MD, 0, 0. So in SU2, this product here is just going to be MU plus MD times pi naught squared plus 2 pi plus pi minus. And I'll just write it down also for your memory. This is pi 0, square root 2 pi plus. So if you square this operator and take the trace, you'll get these terms. I feel like I'm missing a factor of 2. No, sorry. My factor of 2 is mu plus md. That's why it's goofing up. I get, when I square it, you get pi naught squared plus 2 pi plus pi minus on both terms on the diagonal, and then I multiply that by the quark mass matrix, which is mu and md. So this is the factor of 2 I was worried about. So if I, in the isospin limit, if I set these to the same, I just get twice the mass. Okay, good. Now, what do we have? I'm going to pull out specifically 2b, and I'm going to use m hat to denote the average mass of the quarks. So 2b m hat, and then you're left with 1/2 pi naught squared plus pi minus. And now we see this is the mass of the pion, right? When you have a scalar boson in the mostly minus Minkowski metric, your Lagrangian for scalar field theory, complex scalar field theory, has the d phi squared minus m squared phi squared. And then if you have a real scalar, you get the halves. Just as we expect. So we get a real field with a half and a complex field with a 1. So this is the mass. So at leading order, m pi plus minus and 0 squared are equal to 2b times the quark mass. Sorry, m hat. So the pion mass squared scales linearly in the quark mass. As you take the quark mass to 0, the pion becomes massless as we expect from spontaneous symmetry breaking. And here you see it's the same for the pi plus, pi minus, and the pi 0. Even if I explicitly kept mu and md, we see in the mass operator that only shows up in the linear combination. So I don't get anything that depends on md minus mu. All right. Now we're going to start talking about higher order corrections. So before we do, any questions on this so far? Okay, higher order corrections. How are we going to start getting those? Well, that's why I left this expansion of the sigma fields down here. You can see, if I keep expanding this field, I'm going to get more and more pion fields attached to these operators, both the kinetic term and the mass term. So let me just add the kinetic term back here, just so we have it as a reference. All right, let's look at the kinetic operator. So d mu sigma, I just operate d mu on this. And now, when the derivative acts on a set of fields, I do need to remember the product rule. So now, I told you before, the derivative only acts on the field immediately to its right. Well, for the moment, it's going to act on everything to its right. So again, this is context matters. We're being sloppy because we're just taking internal notes for ourselves, and we're not showing our notes as a proof, which a mathematician would reject as clearly not correct. They'd probably say that about most physics, right? All right, so what do we got? These signs with the eyes are going to lead just in the derivative term, just like the mass term, for all terms in the expansion with odd powers of phi to exactly cancel. So this is where symmetry helps you. You don't even have to go through the algebra. You just recognize that they're going to cancel. Oftentimes, when I'm doing this work, though, I explicitly check for the cancellation because it's a way to also check that you haven't made a mistake on something else. Like, maybe you think you got it, but then you actually screwed up some of the combinatorics and your phi to the fourth terms are wrong, and you might be able to find that if you keep track of the odd power fields and see that they haven't canceled. Especially, as you get wiser, you start learning how to program this on a computer to do all this algebra for you instead of doing it on pen and paper. When I was a graduate student, I felt like I needed to do it all on pen and paper to understand it, and then slowly I was like, well, maybe I can use Mathematica. Oh, okay, that makes it so much easier. These days, I try to do it in Python, but like I said, I have not yet figured out how to use SymPy. All right, so our kinetic operator. Let's start with just the term. Also, you'll see I start dropping the covariant derivatives on, or the mu's on the covariant derivative. The mu's on the derivative operators because I know they're there. I don't have to write them every single time. And we all like to joke, we're all lazy. We want to minimally write stuff down. And I'll get into the dot notation soon. What do we get? Okay. So you get d phi over f squared coming from derivative acting on the expansion of sigma and another one acting on the expansion of sigma dagger, and you're taking the product of those two, right? Because I have d sigma dagger, so I have to look at the product, and what we're going to get at order of phi to the fourth. First, we get the phi, but then we'll have a phi times a phi cubed, and then we'll get a phi squared times phi cubed times phi, and that's going to be all the terms we need to go to 4 pion fields. So the first higher order effect will come from having 4 pion fields instead of 2. And 6 pion fields are going to give you even higher order effects, right? So if you think about the mass, if you have an operator with 6 pion fields, and you're going to think about the spectrum, you have to take 2 of them and tie them together to get something that looks like a propagator for a pion or a particle. And so that's a 2-loop integral. And as we'll start talking about, you should be able to quickly see how this must be higher order than the 4 pion field where I tie 2 together. you can do some loop counting and count the powers of the pion mass that are showing up and see exactly how much higher this is than this. So we're just going to work to 4 pion fields. What do we get? So what I've already done is used the property of the trace to make these two terms the same, even though one comes from d phi in the sigma and then d phi cubed in sigma dagger, and the other one comes from d phi and sigma dagger and d phi cubed in sigma. But because of the trace, I can just reorder these terms however I want. And then if we focus on just the powers at phi to the 4, I don't want to worry about the kinetic term because we already looked at that. What do we get? We get 1 over f to the 4, which we are confident in because the phi field has mass dimension 1, and we have to have this is a dimensionless object we're looking at. And you get 1/4 d phi squared minus 1/3 d phi cubed. And now I have to do the product rule and see how these act on the pion fields. So I'll just do one step. So I get I'll resort to my dot notation now. So I get a phi dot, derivative hits the first pion field and not the second, and then same in the second operator. And then I have to add the term where it hits the second pion field in the first term, it's still the first and the second, and then go back. You all know how to do the product rule. Did I do that right? No. And then the same thing with the other operator. Then you can use a trace to move everything around, and you can show that this is equivalent to 1 over 24 f, sorry, the Lagrangian operator. You can show that the 2 derivative term at order phi to the 4th is equal to so this is a commutator. So these are matrices again, remember. So this is exercise for you to do, how to go from here to here and convince yourself that this is right. And if I just write this out to something that might look more familiar as you're along the way, you get 1 over 24 f squared d phi oh, maybe the dots are easier to see anyway. So these are different because these are matrices. And so this is what you're going to get. And then what do you see when you actually work this out? So you either do the math yourself or you ask some computational tool to take the trace of the matrices for you. And you end up with in all its glory pi naught squared d pi plus d pi minus plus pi minus pi plus d pi 0 d pi 0 So you end up with a whole bunch of terms. So here I have, these are all, if you think about what these would look like at an amplitude, they're all terms that would look like this. It's 4 pion fields, but I have 2 derivatives. So then you might come up with some way to note where those derivatives happen to be. And you want to label the momentum of your particles, because if a derivative is acting on one of the fields, you have to bring down the momentum of that field. So let's actually use this. What are we going to do? So let's use this Lagrangian to calculate isospin 2 Iz equals to pi scattering. Because this is a few body workshop, so we have to do some multi-body stuff. It's the easiest thing to do is to calculate Iz equals 2 or minus 2, because then we know initially we have 2 pi pluses, say, and finally we have 2 pi plus. In the initial state, it's pi plus, final state is pi plus, pi plus. It's the simplest thing you can do. You know all the other Iz components of the I equals amplitude have to be the same because of the symmetry. So why don't we just do the easiest one, which is always either maximal or minimal isospin. So which of the operators in this Lagrangian will contribute to this scattering amplitude? Immediately, we can eliminate anything with a pi 0 in it because there are no pi 0s in the initial or final state, and we're not working to include loops in our calculation. And so the only operators that will contribute are these 2, and then there's a third one somewhere. Maybe I wrote something down wrong. One, 2, there's 3 operators up here. Apparently I can't see with or without my glasses. Where's my third charge pion operator? I misread my notes, that's the problem. These are plus and minuses. So I get pi 0s, so two derivatives on charge pions and pi 0s with none, 2 derivatives on pi 0 and nothing on the charge pions, and then I have the term with derivatives on charge pions, and I have all charge pions, and then here I have a mixed derivative on a pi plus or a pi minus, and here they're both on the pi plus or both on the pi minus. So those are the 3 operators we need to track to calculate this amplitude. First of all, can everybody actually read this? Am I writing big enough? Is anybody having a hard time reading it? How about that?
Yeah, a little bit bigger would be better.
Okay. Going forward, or should I write this one bigger? Okay. So, just to say it out loud, pi minus, pi plus, d pi minus, d pi plus, operator 1. And then the other 2, same, except I have a half, an extra minus sign, and then the derivatives are only on the pi plus or only on the pi minus. And now I will write bigger. Okay, so our Lagrangian contains those operators. And remember, the rule is when I calculate an amplitude, at leading order, this is easy. I get my external states. So I'm interested in a state that has 2 pi pluses in the final state. Remember, I have to label them. And then I have I times my Lagrangian. And this is my second order Lagrangian with 4 pion fields coming from the kinetic operator. And pi plus 1 and 2. So here's my amplitude. And again, I just have this insertion of I times Lagrangian, because if you imagine doing perturbation theory in the interacting Lagrangian, you have this e to the I d for x Lagrangian interacting. And this you write down as 1 plus I d for x interacting Lagrangian plus higher order terms in the expansion of the exponential. And so thinking back about the partition function, remember if I have an extra operator in the partition function, that's representative of calculating some correlation function. So that's why I get this IL. And then also I know I'm calculating an initial and final state of pi pluses. So if you were thinking in this partition function language, you would have given a source to the pi plus and the pi minus field, so you can differentiate with respect to that source to create these states as well and bring all those operators down. And I'm just going to skip all of that. I'm saying these words just so hopefully it sticks in your brain somewhere in the back as you're learning how this goes. All right. Let me take a brief aside to talk about the derivative interaction again. We've talked about it once, and Sebastian talked about it, but it doesn't hurt to repeat. This is in position space, and I'm also hiding the fact that I'm working in momentum space, so I've gotten rid of all those integrals. These are things that, you know, in the standard field theory textbooks, they carefully walk you through going from position space correlation functions to momentum space, and you get the energy conserving delta function at the end, and all the derivatives are gone, and you're going to be left in momentum space. Thank you. So, just as a reminder, if I have a derivative acting on a field, and this field has some momentum, so I have, this is the state, and this is the operator, the annihilation operator that will contract with the creation operator of this state. This is going to give me minus I k mu in my Feynman rule. And if I have an outgoing state, this is going to give me plus I k mu. So basically, when you have a vertex, if the momentum is flowing into the vertex, that's going to be the minus I. And if the momentum is flowing out of the vertex, you're going to get a plus I. And you see that if you imagine having a charged scalar field, and you do the Fourier decomposition. Here's some more shorthand for you. We have the annihilation operator, e to the minus I k dot x, plus the creation operator. And this is how we see, we use the annihilation operator to annihilate with the creation operator of an incoming state. So the annihilation operator has the minus ik, which is why we get the minus ik mu. And if we have an outgoing state, we need the creation operator to annihilate with the annihilation operator of the final state. That creates, right, the final state is created by vacuum with an, with an annihilation operator. And so I need the creation operator to talk to this guy and contract and give me a 1 so that I get something that doesn't vanish in the Wick ordering, the normal ordering of the Wick contractions. And so then I get a plus ik. All right. Extra little shorthand, this d3k bar is d3k over 2 pi cubed. I'm just borrowing the bar from the h bar to put it on the k. All right. And then if you have a derivative acting on this, then you can just see the derivative commutes through the integral. This is an ek. So then you get minus I k mu a e to the minus I k dot x. Okay. So coming back to our Lagrangian and our amplitude, what do we get? So now we have these operators. So we need to work out the Wick contraction of these operators in this matrix element. So let's look at the first one. We have pi 3, pi 4. They're both plus. And then I have this operator that looks like d pi plus, d pi plus, pi minus, pi minus. And here, recall, the pi minus is the contains within it the creation operator and the annihilation operator. Wait, hold on, what am I saying? The pi minus right. I just confused myself for a second. Sorry, hold on. I'm wondering if I have a mistake in my notes. Okay, I think I have a mistake in my notes. It's just flipping pluses and minuses on the pion fields. Just give me a second. The notes were written before karaoke last night, so you can't blame that. Oi, this is terrible. Okay, yeah, okay. I'll have to fix this on the fly, so you're going to have to keep up with me now and correct my mistakes, because I'm not going to maybe get all the corrections correct. All right, so this one, I mean, it would have been fine to leave it like that, but. So I have the pi plus, pi plus, pi minus, pi minus. Now I need to create the pi plus state, which is going to have the annihilation operator, or the creation operator of the pi plus, which happens to be a pi minus, and those two things will contract. So now, what do? These counting rules, the Wick contraction rules. So when I make this contraction, remember I have two choices of how to bring this field in. Because this pi plus can either go to pi 1 or pi 2, and it cannot go to pi 3 or pi 4. And so I have a factor of 2 that comes from that. And in addition, I have to bring down a derivative. And similarly, on this side, I have two choices of how to do the contraction. And then after that, there's only one choice for the others. So the whole rule gets me 4, and now I have a momentum coming in, so I get minus I P1, and then I have another momentum coming in, so this gets dotted into minus I P2, which is minus 4 P1 dot P2. Okay. Now, let's look at the other two operators. Same thing, except now the derivatives act on the external states, and so I get a plus, but plus I, so I get the same minus sign, minus 4, but now P3 dot P4. And then I have the mixed term, which we can write as now here I get a factor of 2 in choice, but now that factor of 2 turns into I get a P1 or a P2. So I don't get a factor of 2 there. And the same thing over here, I get a P3 or a P4. And here I have an outgoing momentum, so I have a plus I. Here I have incoming momentum, so I have a minus I. So the i's in this case give me an overall plus sign. And now I get P1 plus P2 dotted into P3 plus P4. So the first one gets a P1 or a P2, and I have both those terms, and the second one, P3 or P4. Perfect. Now, P1 plus P2 is equal to P3 plus P4 for momentum conservation, which is equal to the total momentum of the system. And as you recall from the other lectures, this total momentum squared is just the Mandelstam variable S. And then from your exercises also, okay, P1 dot P2 I can write as 1/2 P total squared minus P1 squared minus P2 squared. Right? So then I get another S minus, now they're both the same particle, they're degenerate, and they're external states, so they are on shell. So I set these equal to the on-shell external mass times 2. Thank you. So then, if we add it all up, what we find is we get an I over 6F squared, because we're getting the Lagrangian. I guess I've pulled out a factor of 1/2. And I get I over 6F squared, and then I have minus 4 S minus 2 M pi squared, and then minus 2S. So, and I guess I can take out a factor of 2. So, what is the amplitude in the massless limit? So if we consider the massless limit, remember S is equal to the total energy of the system. And let's work in the center of mass frame to make our life easy. So in the center of mass frame, where we have equal and opposite momenta, S is going to be 2E 0 vector squared, which is 4E squared, which is 4 M squared plus P squared. So if we go to the massless limit, it's just the momentum, and then our amplitude see if I got all the factors of 2 right. It looks like I forgot some 3 or something, right? S, so there's a 3, 12 over 2 is a 6. Yeah, I think I just got this wrong in my notes.
Yeah, I think this is correct. I think there's some.
I'm sure this is correct, because I know the later answer.
Well, then the I over, so you divide it by 2, so that 1 over 2
Oh.
should become 1 over 3.
Sorry. Thank you. This part was correct. Only if that, yeah. All right, good. Okay, 3 cancels, and then I get a 4p squared. Okay, so I didn't make a mistake. I only made a mistake on the board, not in the notes. Good. So, and is this what we expect? As we send the momentum to 0, the amplitude goes to 0. Is that what we should expect? Did we do something wrong? Anyone? Anyone? What do we expect Goldstone modes, scattering cross-section to go like at 0 momentum? They stop interacting. They only interact derivatively with momentum. So this is exactly what we expect. Good, we haven't screwed up so far. All right, now let's add the mass and see how the mass affects the amplitude. So our mass term, recall, again, now we need powers of phi to the 4, and it's sigma plus sigma dagger, so the only term that will contribute is this last one. So I still have this flavor trace to deal with. The 1/12 is 1 over 4 factorial, so 1 over 4 times 3 times 2, but I have 2 of them, so I get rid of the 2, and it's just 4 times 3, so I get the 12, and the sign is plus, and here we go. So this is equal to b over 24 f squared, trace the quark mass times phi to the 4. And this you can show is equal to b over 24 times mu plus md times pi naught squared plus 2 pi plus pi minus all squared, which is otherwise known as 2b. Now I'm going to combine mu and md into m hat. And then I trust you can work through the algebra, and then you get pi plus pi minus squared plus pi minus pi 0 squared. And then there's a quarter pi 0 to the 4th. So there's only one operator that contributes to our amplitude because we're doing isospin z equals 2. So we only get the pi plus pi minus just like before. Let's do the Wick contraction factors. So now we have this pi plus pi plus. There's no momentum left on the field and field operators. I'll just draw the number anyway. So again, 2 choices how to do this, 2 choices how to do this. So the whole thing gives me a 4. And then if I put in the full Lagrangian term, I get 4 times 2b m hat over 6f squared. So then the contribution to the amplitude, I guess I can erase over here. How's my time? Am I already over? Ah, darn it. No loops today, damn it. Okay. Here I was trying to talk fast. Maybe I was talking fast. I can tell you my story when we're done. All right, final amplitude. So the amplitude from the mass term of this second order operator is going to be 2b m hat over f squared times 2/3. So then if we add it back to the other kinetic operator, the full amplitude for isospin 2 is going to be this quantity. Now notice I've kept separate m pi squared, which came from the on-shell external kinetic derivatives from this 2b m hat, which is the pion mass at this order. Because when we go to one loop order, which we're not going to do in this class, but if you were to calculate the scattering amplitude at one loop, and you wanted to consistently count all the contributions, you would have to remember one of these is a leading order mass, and one of them is an on-shell mass. And so if you want to express the whole expression in terms of on-shell pion masses, you're going to have to add the correction to turn this into an on-shell pion mass. So this is just something you have to keep in mind when you're doing this perturbation theory. It's important to keep track of on-shell terms and bare terms in the Lagrangian. But for now, let's set it equal to the mass. So this is 2 m pi squared. This turns into a 6. And so then what we can see is the amplitude becomes 3s minus 6 m pi squared. And then if we take the limit that the momentum goes to 0, so as p equals 0, s is just going to become 4 m pi squared. And so you can see at threshold, a is going to become minus 1 over 3 f squared. I get 12 m pi squared minus 6 m pi squared, which is otherwise known as plus 6. So it's minus 2 m pi squared over f squared. And then the last thing I'll say before stopping is you can then ask, what is the scattering length? Because we can connect this to the amplitude. And so the reason I went to threshold is because at threshold, all the terms in the K matrix, so the inverse K, the amplitude, say, scales roughly like 1 over K cotangent delta minus IK. And at threshold, K cotangent delta is equal to minus 1 over the scattering length. Minus is a nuclear physics convention. Oftentimes you'll see this with a plus, and we can talk later about why that is. But at the end of the day, let's just say it's minus here at threshold. So this is at K equals 0. And so then we can ask what the scattering length is in the S wave, and then it turns out that you get m pi a. So a is often used for the scattering length. And I'm multiplying it by the pion mass such that this is a dimensionless quantity. These are always the nicest thing to use for lattice QCD, dimensionless quantities. This is going to be given by m pi squared over 4 pi f squared. So this, as we'll see next time, in fact, is the small expansion parameter of our theory. And so the leading correction for the scattering length of the isospin 2 system is some number pi times our small expansion parameter. And it actually works remarkably well when you compare it to lattice calculations at unphysical pion mass. This formula works at few % accuracy. It's kind of cool. All right. I'll stop there for now.
All right, let's thank André. All right, before coffee break, do we have any questions?
Yeah, you can't get coffee till after you get
there's
your picture taken.
Okay, so we have a photo first, but before the photo, any questions?
So again, I'm hoping to provide you with an algorithmic recipe to do these calculations, even if you don't fully understand it. So I hid my errors from you in my notes. I'll correct them before I send my notes out. But I will also send the notes out, by the way, as well, so you can compare the notes you've taken to the ones I'm writing. And they will have some words in them, not just equations.
All right, I don't see any questions, so thank you, André. Where are we going for the photo? Okay. All right, so let's all congregate out there. And then coffee.